So for today's session, we are going to take a closer look at the programming side. We are going to mainly use one of the software stacks I mentioned previously back in Wednesday, that is called Pulsar. But before we go into much more detail on that, I wanted to go through a quick refresher from some of the key elements from last week's session. So let me just share my screen for that. Let me know if you can see my screen.
Yes, we can see your screen.
Perfect. So as part of a refresher, we are going to quickly go through once again the main components in working with a neutral atoms type device, because these are the main elements that need to be represented in low-level implementation cycle as well. So, as you recall, a neutral atoms type quantum computer is an optical installation that uses various different lasers to trap and then to manipulate atoms on an individual scale. The whole setup itself consists of the vacuum chamber or science chamber, also the part on the right, which is the heart of the quantum computer. It is inside this vacuum chamber that we are trapping and manipulating the atoms. So the trapping itself happens by a first set of lasers that do the MOT, so the magneto-optical trapping, creating focused refracted laser light at specific positions in currently a vertical plane in which we want to trap individual atoms. So that's the first main component, is having the atoms in the right positions in order to start off the actual computation. And then once the atoms are trapped and are in the right positions, then the second set of laser gets activated that sends energy, that sends information to this atomic register, to this quantum register, to this collection of atoms, in order to excite the system, to instill an evolution, ideally a more complex evolution. And the computation itself is encoded in this evolution cycle. And we discussed this on Wednesday that basically this boils down to multiple different cycles. The first cycle being catching the atoms, so trapping the atoms itself. So that's what's referred to here as layout loading. So ensuring that you have atoms, you have sufficient number of atoms at your disposal before starting the computation. Then comes the register preparation, in which you use optical tweezers to move around the atoms from traps in order to ensure that you have atoms at the right positions. So up until this point, everything is automated inside the quantum computer through integrated operating system it is handling. So this is the part that developers don't need to focus on. They only need to focus on defining the actual register, defining the positions where they want to have the atoms. It's up to the machine to make sure that it catches enough atoms and it manages to move the atoms in the right positions. So once the atoms are in place, the actual quantum processing, so the actual computation cycle can start, which involves subjecting this quantum register into the specific laser impulses defined once again by the programmer, by the user, in order to instill some kind of evolution. Throughout all these phases, multiple images are being taken with fluorescent imaging in order to verify the position of the atoms and then provide for a readout. As you recall, the readout itself consists of measuring through this fluorescent imaging the photons emitted naturally by the atoms, and it is through these emitted photons that we are able to decipher, we are able to obtain in which traps atoms are still present and which traps atoms have escaped. So after the computation cycle itself, indeed, certain atoms are allowed to escape. This is due to the fact that during the computation process, we are sending energy to the system, and through this dynamic evolution, if the atom has sufficient energy and maintains sufficient energy, it is able to leave the trap because the magneto-optical trapping is set up to keep the atoms in place only in their ground state. So it is parameterized, it is set up in specific frequencies in order to trap our rubidium atoms in their ground state and the position. However, if they gain sufficient external energy, they are able to escape this energy well, this trap, and then they disappear from the computation itself. And this disappearance, these missing atoms provide information, as it's indicated here, when we see dark spots on the image itself. So when we see that atoms are no longer present where they were initially present, that is the information that it became sufficiently excited. Therefore, we can read out one correspondence to it, contrary to the zero information that you would obtain from atoms that are still present in the trap. Of course, this, much like with any other quantum computer, is a trace of what actually happens with the quantum system. In actuality, we do not really know if the atom has reached its hyperexcited Rydberg state or it has maintained this state. We know that it just got sufficiently excited. Therefore, you need to repeat the experiment on multiple occasions to gain a better understanding of the underlying quantum information. With that said, last week we looked quite extensively at Pulsar Studio, so a graphics user interface, an open access graphics user interface that was built to allow for basically no-code environment to work with neutral atoms type systems to design the first experiments. We did a series of explorations, not only from a physics perspective, using the antiferromantic state experiment as an example, but also we have looked at a potential representation of it through the language of graphs by encoding a solver for maximum independent sets type problems. So we are going to start today's investigation by looking at this tool once again and examining a bit further one of the tabs I haven't really touched upon, which is the actual automated code generation feature that is included in this tool. But for that, let me give you a brief introduction for today's main focus. So the software stack we are going to focus on. As I mentioned, currently from Pasqal side, we have two open source Python libraries available. So anyone can download and use them in a dedicated Python environment. We are going to focus on Pulsar, which is the low-level coding environment. It's really the lowest possible interaction that an external user is allowed to have with either an emulator or with the actual physical quantum computer. Pulsar is really meant to provide all the required access and to allow for all permissible manipulations on a neutral atom system. So it allows you to define what type of quantum computer you are working on, be it a physical device, a digital twin of a physical device, or a more artificial virtual machine on the back end. And based on these parameterizations, it only allows for sequences for code to run if it is physically permissible. So it is really a physics-driven and physics-based software tool that is tailored for neutral atoms type systems, accounting for the additional flexibility you need to have when you design experiments due to the fact that contrary to other types of physical systems, a neutral atoms type system allows you to place your physical qubits at given specific or much more flexible locations. So this flexible architecture is typically not featured in most of the other quantum computing archetypes. Therefore, the programming language needs to be ready to handle it and allow for permissible placements of the physical qubits inside. As an outreach, there is a second software stack that offers a much more higher level interaction called Cadence. It's also an open source Python library that's tailored for analog and digital quantum computing, specifically with neutral atoms, but not just with neutral atoms type systems, as there are some compatibilities with other types of technologies. It is to be viewed sort of as an equivalent to IBM's Qiskit toolkit that we have taken a brief look at on Wednesday. And it is particularly tailored for machine learning synergies and machine learning based executions. Therefore, we are going to focus on Cadence during the Friday session, where we are going to look at graph machine learning based applications and algorithmic implementations in particular. But for now, we are going to focus on Pulsar itself, and namely on the key features that Pulsar offers to design your experiments themselves. For that, we're going to go through a series of Jupyter notebooks that I've prepared. But before launching into those notebooks, I wanted to briefly showcase a very important resource that's at your disposal, which is the Pulsar documentation. So if you go on the web and just type Pulsar or Pulsar documentation, you will end up on the landing page of Pulsar itself. That gives you access to multiple available resources. So there is a dedicated publication, 70 or so page long publication on the Pulsar software stack that goes more into detail of how the software environment is set up and what are the basic principles that it's being followed. As I mentioned, Pulsar is really based on the physics of a neutral atoms type system to only allow for physically admissible manipulations. Therefore, in the publication itself, it's discussed much more into detail how the particular components are being handled and what are the fail-safes that are being implemented. Other than that, because it's an open source tool, you can directly go and access the dedicated GitHub repository with all the latest versions at your disposal. The landing page for the website itself serves as an installation guide as well as an online documentation that is still being expanded as we speak to allow to showcase even more features of this software toolkit. But already you can find a lot of very varied information dedicated in different types of sections. So for today's notebooks, we are going to go through some of the key components that are elaborated in the documentation much more. So if at any point you have questions, first of all, feel free to ask them. I will try to stop at strategic points to answer the questions themselves. However, on top of that, if you're interested in knowing more about certain parts, certain components that I mentioned, you are free to cruise through and look deeper into those elements through the actual documentation. With that said, let us turn our attention back to Pulsar Studio, first of all. And I've taken once again one of our go-to examples, so the antiferrometric state experiment. One of the key examples available in Pulsar Studio that we have seen can also be interpreted as a graph-based formulation. We have been looking at the following setup, which provides for, on the top left part of the screen, the placement of the atoms. So this interactive environment that allows you to move around the atoms themselves. We have looked at extensively on how to design the pulses themselves, how to create specific laser pulses and what the different components allude to. What we have looked a bit less at, but I did mention that the feature is included, is the code side of Pulsar Studio. Indeed, by default, Pulsar Studio is really meant to provide for a code-free or a no-code interactive graphics user interface. However, as the name implies, it is really a tool built upon Pulsar itself. So behind the scenes, it is the open source library Pulsar that is running. More specifically, so in Pulsar Studio, you have a specific code environment. When you load up the tool itself, it might be at a separate window, but you can move it together if you want to hide it, which provides sort of a minimal working example Python script of the corresponding experiment you have designed without the code itself. So let us first go through the main elements that are present in this Python script. It is really a Python script that is getting automatically generated and can be reused in an actual working Python environment if you want to build upon the code section or the experiment you have designed with the visual interface. So as with any Python script, it starts with loading a couple of the necessary elements, necessary components from Pulsar itself. So if you take a look at the first line itself, so from the main Pulsar library, it imports, it loads three important components. The first is the register object, which corresponds to the atomic register. So the placement of the atoms will be stored in this component. It loads the sequence object, which will serve us to define the laser pulse itself, which will then be compiled and concatenated into a pulse object that can be subjected and defined for the experiment itself. There is a specific subdirectory that handles the predefined virtual machines and backends, as well as it allows for you to load and define new virtual machines. So for this experiment, the default mock device, so a simplified virtual digital twin of the machine was proposed, and therefore that is what's being loaded. And it automatically loads the specific components required to define the laser pulse you have selected in the parameterization itself. What I mean by automatic code generation is true for both the register design and the pulse shaping itself. And the code structure itself follows really what we have discussed previously on the main computational cycle. So if we go back to the visual representation, the first component is to define the register layout, to define where we want to have the atoms. Then these atoms will be subjected to the processing cycle, so to the actual computation cycle, through the defined laser pulses. So throughout the coding, throughout the implementation cycle, you follow these two main steps. So first, you define the register itself through the graphics user interface, which can get automatically updated. As you can see, it highlights in the code which atom I am working with currently, and it is updating automatically the coordinates. So what's proposed here is the simplest way of designing an atomic register, which is allocating specific coordinates to specific atoms and labeling them one by one. We will see some other ways to generate the atomic register a bit later on. This is just to highlight what I would say is the most straightforward way to define the atomic register. Once you have defined the atomic placement, the components themselves, the next section is designing the pulse itself, the laser pulse itself. So the component called pulse shaping, which involves defining the different parameters and how they evolve throughout the time component itself. So as we have discussed last week, there are two main components that you need to keep in mind when you design a neutral atom-based experiment. For a laser pulse, the two physical parameters that play a role is the amplitude parameter, which is represented by the top side, the purple curve, corresponding to the source term in the operator representation of your experiment, and the bottom side, which is the gray experiment, corresponding to the detuning parameter, which is the sync term in the one-body interaction side of the Hamiltonian or operator formulation. As you can see, there are different components that have already automatically been defined based on the shape that we have given. So we have a Blackman waveform, which is a Gaussian, a truncated Gaussian waveform that it is using to build the amplitude parameter. So this is the top part. It defines how you build this specific laser pulse, this Gaussian curve-based laser pulse, and then allocates the necessary physical parameters to it to design this specific shape. It does the same thing for the detuning, although you have two main components due to us stopping the evolution of the detuning partially through the experiment. That's why it has two components that are being concatenated into a single detuning set. And then the script stops at drawing out the whole sequence, so providing a visual representation of this tool that is, in this case, being much more interactive than it would actually be. So with that said, again, to get started with any kind of neutral atoms-based coding or with Pulsar-based coding, Pulsar Studio can be a good component in designing some kind of experiment that you're interested in. If you're not sure where to start, you have a couple of examples in Pulsar Studio, or with the Pulsar documentation, you have some basic examples as well for different types of experiments designed, and the documentation itself is really viewed as sort of an integrated Jupyter notebook. So it actually provides for the required code. So if I were to load the specific section of the documentation on optimization, so in this case, the quantum approximate optimization algorithm and the quantum adiabatic algorithm is being discussed here. We are going to take a closer look at this section on Wednesday's session, which is dedicated to optimization in much more detail. But as you can see already in the documentation, you have the necessary coding elements. It's really an integrated Jupyter notebook that you can load as is and work with if you prefer. With that said, let us now take a closer look at how you would start off working with Pulsar as a coding environment. So once again, the two main features you need to keep in mind when designing an experiment is placing the atoms. So designing the quantum register, the atomic register, and then defining the laser pulses, the parameterization of the laser pulses with which you want to interact with said system. So the programming itself, it really happens at this very, very low level. Therefore, you really have access to all the tools necessary to design experiments at this, level of abstraction. It's not necessarily the most practical way of programming because you really need a good understanding of the physical parameters to design especially more optimal cycles. And it also relies on you having access to the exact mathematical formulation of the problem that you want to encode, which can be quite challenging depending on the type of problem you are dealing with. For today's session, we are going to keep it relatively simple. At the second half, I'm going to show you a maximum independent set type basic graph example and the algorithmic implementations you can design for that to illustrate how it would work in action. And then for the later sessions this week, we are going to take a closer look at much more elaborate algorithmic schemes. So for now, let us look at the first component, which is designing the actual atomic register, so placing the atoms themselves. As Pulsar Studio itself illustrated, one way to define the register is to define the coordinates themselves. So individually for each quantum bit, define the positions themselves. Here, what I've done with a very, very simple Python script is that I've defined an equidistant square lattice, a 4x4 square lattice, and I'm going to ask Pulsar to load the atoms according to the coordinates that I've designed with this. So as to give you a better idea what the coordinates look like, I've drawn them out to illustrate that we have this 16 coordinates defined through the Python script, and then I simply pass this object, so in this case it's in a dictionary format, so once again a label of a qubit, and then the coordinates themselves, and followed by a label and the coordinates associated to that. I can pass it directly to the register object, and I can ask it to draw to get a visual feedback. And as you can see, with Pulsar already, there are some visualization aspects that come with the package directly, so you can get a direct visual feed when you start designing your experiment. So you don't need to rely on Pulsar Studio to get a better understanding of the code. At different points, you can visualize the key components of the of your implementation already. As you can see, I have in total 16 atoms, 16 traps in which we want to have the atoms, which will correspond to our physical qubits. It is equidistant square lattice placement, and that I've chosen as an example. This is not the only way to define register. So you have other ways of doing it. So this relied on the fact that I was using a dictionary in which I labeled the atoms by numbers themselves, but I might not require to do that. So if I go back to just the collection of coordinates as an object, I can load it directly by specifying that I'm just loading the corresponding coordinates and tasking Pulsar, tasking the register object to allocate labels, to allocate name tags to each individual atom automatically. So as you can see here, instead of loading the dictionary object, I've just loaded the collection of coordinates themselves. I have as an parameter, I can give what naming convention the tool should use when they index, when they label the atoms themselves. Since they correspond to physical qubits, a good practice is to name it with Q something. This is typically done in most quantum-oriented programming environments already. And it has generated the atomic register for me, labeling in this case automatically for the square lattice given the coordinates, but in this case the labeling was chosen by the software tool itself. So this is a second way of going about if you don't necessarily require fine control of how you name them. You can just directly pass the coordinates without having to rely on a dictionary. Alternatively, and especially for structured grids, so for specific geometries, you can rely on some of the built-in methods that can generate layouts, that can generate geometries based on a couple of key parameters. So in this case, since I'm working with a square lattice, there is a specific command in the register object called square that allows you to design a specific sized atomic register based on a square lattice placement. So it can be square or it can take a rectangular shape. Both are admitted if you define the parameters correctly. All it asks for is the spacing, so the distance between two neighbors, which is all you need to know to design or a symmetric regular atomic register of this shape. For it is true for the square lattice structured grid, and it is true for other allow structured grids as well, that you only need the spacing and the dimensions themselves. And as you can see with these two parameters that I'm asking for 4 or 4 by 4 square lattice with a spacing of 5, it automatically generates this square lattice itself. In the documentation, you can see some other examples for structured grid generation. Typically, triangular or square-shaped lattices are allowed for automated generation. Otherwise, the coordinate-based definition offers much more flexibility because you don't necessarily need to input the atomic placement in a structured fashion. You can really define the geometry itself as you would want, as flexible as you want. Bearing in mind that contrary to Pulsar Studio, that has some physical restrictions, so if here I can move around the atoms, and the tool itself stops me from moving atoms too close together. As a reminder, this feature is there to prevent, physically speaking, two magneto-optical traps from interfering with each other. So you cannot place two traps too close to each other, otherwise they would jeopardize each other's functioning. They would reduce the quality of the trapping in between them. So in pulsars 2D, there is a built-in feature that forbids you from doing that. When you're working with pulsar itself, of course, the tool cannot forbid you from wanting atoms at specific coordinates. However, you will get warning if you are too close, and then you will get an error message if you are within the specified distance. The error itself will not happen in the register design itself, because as you have seen, at this stage, you are purely working with the geometry, and at no point have you defined the actual machine, the actual backend you would want to work with. That would happen once at a later stage when you compile together the pulse and the laser and would start the execution itself. Then you would get an error message if you have defined a layout that is not compatible. Nevertheless, if you were to move two atoms suspiciously close to each other, even within register, the register object, there are some fail-safe that can warn you that you have two atoms, two physical qubits way too close to each other, independently of the actual device you would execute the code on. Otherwise, the warning and the error message would come on the moment when you are allocating the register to the actual virtual machine, or when you would send the code to a physical device, you would get back the error message that the register you designed is not compatible with the permissible geometry itself. Okay, yeah, so that's that for the geometry itself. Let's take a quick look. I see yeah, so for now, I'm just going through some of the key elements of designing pulsar experiments themselves. So you can find all the code on the online documentation, not in such a grouped and organized manner, but in different pages from the getting started. From the fundamental concepts and going through classical and advanced features. There is no, I can make the notebook available if that interests people. Of course, that's not a problem, but all the resources that we are using are just a concatenation and a restructurization of what's presented on the online documentation as well. So don't worry too much on the actual live programming itself. But at any point, especially for this notebook, the commands are simple lines. So following it, if you have Pulsar already installed, should be quite easy itself. So moving on, once you have the geometry defined, the next step is to start designing the actual experiment. So to start defining how you would want to interact with this system. For this, you would first start by loading your backend, in a sense, loading the machine that on which you would want to work with. So for this, you are defining a sequence type object. So the sequence sort of connects the register, the atomic register, the physical layout you previously defined with a machine. So it sort of inputs the layout to the machine. And then you will be able to start designing the pulse shapes, the laser pulse shapes themselves for the interaction site. So if you had any constraints, any issues with the geometry, at this point, you would definitely get warning error-based feedback if you did a non-permissible operation, as I mentioned before. For today's tutorial, for today's exercise, we are going to mostly use the digital analog device. So this is one of the predefined devices in Pulsar that come with Pulsar itself. It is not the only device at your disposal. Here I mentioned we have already seen mock device, which is the default one in Pulsar Studio, and you can see its parameterization on Pulsar Studio. Other than that, the two main digital twin backends that are currently available is analog device and digital analog device. So analog device is the preferred device, the preferred physical backend to be used when you design purely analog experiments. So its physical parameters are set to be compatible with the first generation quantum processing unit of Pasqal. So the code you would design on an analog device that runs on your local emulator will run on remote emulators and on the physical quantum processing unit as well. Digital analog device, on the other hand, allows for both analog and digital, so quantum logic gate-based implementations. However, since it's a low-level programming tool, you are not directly calling up on logic gates. You are designing the pulses, you are designing the signal that would reproduce the same effect as a logic gate would. So you are one layer of abstraction lower than you might be used to, which can make the programming with logic gates a bit more challenging. Nevertheless, it is something that is actually possible. We have seen a couple of examples last week on Wednesday, and you can find in the documentation specific dedicated tutorials. So for instance, you have a detailed explanation of how you would build a control set gate, and you have discussions on rotation gates and NMR type gates as well throughout the documentation itself. We are going to focus on digital analog device for this showcase in order to illustrate the different types of laser pulses you can define and the different channels on which you can define these laser pulses. Indeed, that's going to be the first element to start working with. So once you have selected the device, the machine on which you want to code or for which you want to design your experiment, the next step is to select the physical channels. So the channels are the ways of interacting with the atoms. So you can query the available channels for a specific device by the available channels command. So for my sequence that I designed for the aforementioned square lattice and for the digital analog device, if I ask for what channels are available, it's going to list me a couple of physical ways of interacting with the atom. So here I have Rydberg global, Rydberg local, Raman local, and DMM0. So it lists me 4 different options. for the channel, and it also provides all the physical parameters and constraints for each of the individual channels. So you have information on maximum permissible physical parameters, so maximum detuning, maximum amplitude. You have information on how long your experiment can last, so the time factor, and you have also some minimum constraints defined as well. So to give you an idea of what these different channels refer to, the Rydberg global channel refers to the fact that in your device you are going to use Rydberg type hyperexcitation. So you will be pushing your atoms to large energy regimes, the Rydberg states, and the global modifier or label refers to the fact that you are interacting with all of your atoms, all of the atomic register at the same time. So that's why it's global, because you are designing a single laser pulse that's shown on the whole atomic register at the same time to instill evolution that can then be varied based on the actual geometry. So the Rydberg global channel is the basic default channel that's available for all of the devices. This is the only channel available for the analog device, because at least in the current version, because that's the only channel that's compatible with the first generation machine. It's leveraging the Rydberg excitation to reach high energy states, and the global modifier is really there to just indicate this restriction of the machine, that you cannot interact with different atoms in different ways. If you want to do that, you need to choose a device that supports the Rydberg local channel. So the local channel refers to a single targeted laser light on a specific atom. So that's why the locality refers to the fact that in this channel, you will be interacting on an individual atom level. Otherwise, you will still be mobilizing Rydberg type high energy hyperexcitations. So as a reminder, this is the channel you would be using to instill entanglement on especially local entanglement when you would want to build quantum logic gates. So this was the channel, one of the channels we used to build the Control-Z sequence, for example. The third channel is the Raman local channel. So the Raman, contrary to the Rydberg state, refers to the hyperfine excitation state, so a low energy excitation state that is used to typically map single qubit logic gate interactions on a neutral atoms type device. So Raman refers to a low energy excitation state. Rydberg refers to a high energy excitation state. A local designates that you will be interacting with individual atoms, and global designates that you will be interacting with all of the atoms at the same time. And finally, there is the DMM channel. So here it's DMM0, which is an intermediate type channel that allows for you to do what we call detuning modulation map. So detuning modulation map is sort of an in-between between global and the local channel. An in-between in a sense that it allows you to manipulate the detuning parameter locally, while you have to manipulate the amplitude parameter globally. So it is sort of a mixture between global and local interaction. So this is what we call physically a partial addressability. So The tool itself doesn't allow you to fully realize, for instance, quantum logic gate-based architectures. However, it goes beyond what you would be capable of doing with using only the global interactions, because you can tailor and modify the detuning parameter on a local scale. So this channel in particular comes into play with optimization type problems because this is the main tool to encode weights in optimization-based problems. And this is also a feature that will be present for the next generation of Pascal's physical hardware. So on the software side, as I mentioned, all of these channels are supported for emulator-based executions. For the physical device, for now, it's on the Rydberg Global channel that's supported. With the new generation of the device coming out next year, the DMM channel will also be supported as well. Once you have gained a better understanding of what channels you would be using, typically that's what dictates which device you would want to choose for your experimentation itself. Again, I've chosen the digital analog device because that's what offers the most flexibility, so that I can really showcase the different parts of the program that you would, for instance, need to define. So with that said, once you have your sequence ready, you define the channels on which you want to work with. So in this case, first of all, I'm declaring a Raman local channel that I'm going to call channel 0, CH0. So the Raman local channel was the main tool to build quantum logic gates, 1-qubit quantum logic gates. So it's a hyperfine, low energy state with local, so individual atomic interactions permitted. Then I also define a second channel named channel 1 or CH1 that's going to be a local channel, but a Rydberg type local channel. So Rydberg again refers to the high energy, hyper-excited states and with a local manipulation, so targeting individual atoms. And for the channels, especially for the local channels, from the declaration itself, you can designate a specific atom that you would be targeting with that particular channel. So here in this formulation, to declare the channel, I've chosen the name, I've chosen the type, and if it's a local channel, I can directly assign which qubit or which number of qubits I want to interact with this specific channel. Once I have declared the channels themselves, I can get a summary of these channels by the declared channels command. So at any point in time, if I'm not sure, if I'm working with a different code, I can just query and ask what channels are defined. So what interactions are permissible and what are the parameter constraints that I need to keep in mind. Again, the channel description gives you a feedback on what are the minimum and maximum parameters values that are allowed. If you were to go in the pulse shaping side outside of these boundaries, you would get error messages once you would start compiling the code itself. So it's always good to keep in mind these different potential restrictions. Once you have the channel itself defined, you can start by designing the actual interaction, so the actual pulses, the laser pulses with which you would want to interact with this. it is at this stage that it's going to be important for local channels to designate what we call the target. So as we have seen here, if we declare a channel, especially for local channels, you have the option to already define what is the target. So on which quantum bit, or either using the label or the numbering, on which physical qubit or we want to interact with that specific channel. If that hasn't been done, that is something that needs to be set before you allocate an actual pulse sequence to that particular channel. So if you haven't done the declaration of the target when defining the channel itself, you can set it yourself with the target command. So allocating the qubit number 1 to the channel 0 that did not have a target defined. Once that's done, so you can start building the actual laser pulses that all take a similar syntax as this is. So here, first of all, to illustrate as an example, I'm going to design a constant laser pulse, so fixed intensity, fixed amplitude, fixed detuning, the simplest laser impulse I can send to the system. So this is done by the corresponding constant pulse function. So this requires a couple of parameters. So of course, for all of the laser pulse designs, you would at least need 3 main parameters to keep in mind. The duration, so how long the laser sequence is going to last, the amplitude or some variation of the amplitude itself, so for the source term, and some variation of the detuning. And here, because in this case, it's more of an optional, but because we are working with local channels, the phase of the laser light plays an important role. So this is also something that you can define. Once you declare the pulse object, then you can just simply add it to the corresponding channel. So you need to define the pulse and add it to the channel so that the program knows where and at what point it needs executing. At the same time, especially if you are working with multiple channels, you might not want to execute in parallel multiple laser pulses. So for example, for this reason, there is a delay option available that allows you to halt the activity on a specific channel. With a print command at any point when you're designing the sequence itself, you can get text-based feedback on what's the status, what laser pulses you have defined. So as a reminder, we defined 2 channels, Rydberg local channel 0 and a Raman local channel 1, or was it the other way around? A Raman local channel 0 and a Rydberg local channel 1. And I designed a constant pulse for the channel 0, and I delayed the activity on channel 1. So the print command gives a textual feed on all the relevant information, but there is also the draw command that allows you to sketch in a similar fashion as you have seen for Pulsar Studio how the experiment itself looks like. So for this initial sequence, we designed a constant pulse for 200 nanoseconds, so it goes until 200 nanoseconds with a fixed amplitude and a fixed detuning parameter for channel 0. And we have delayed the activity of channel 1, but since nothing is happening on channel 1, as we can see, there nothing is indicated here. In the visual representation, you can see a number in orange on the top left part of the sequence, which indicates on which physical qubit you are acting. So channel 0 was targeting the 1, and channel 1 was targeting the 4 by declaration. So this is to add a very, very simple pulse, but as we have seen on Pulsar Studio, you have access to a whole plethora of different types of laser pulses. So all of them are documented in the specific section of the Pulsar documentation, but if you want to get an immediate visual feed, you can just go to Pulsar Studio and look at the different options that are proposed by default. So again, the advantage of looking a little bit more into Pulsar Studio is that it also generates the code for you. So if you were to choose different type of laser pulse that's unknown to you, you can just click on the corresponding visual and it generates the code. So you get an immediate example of what's the syntax to be followed to define that specific type of laser pulse. So it can be a good way of getting into or getting familiar with the different syntaxes. As an example, I'm going to design a new pulse for the channel 1 that has been empty so far, and I'm going to add a bit more complicated one. So something similar to what we had on Pulsar Studio. I'm defining a truncated Gaussian, so a Blackman waveform for 1,000 nanoseconds with a specific area. As I mentioned, for these more complicated waveforms, laser pulses, you need to define more physical parameters to give a better idea. This can be the area under the curve. This can be the peak of the curve. One of this indicator defines the other, physically speaking, due to their mathematical connection. So what I'm defining now here is Gaussian, so Blackman waveform for the amplitude and a simple ramp, so linear graph for the detuning parameter that goes from -20 to +20. Again, both of them are duration of 1,000 nanoseconds. So the waveform themselves can be queried to get different parameters. For instance, the integral, the surface under the curve, which was one of the parameters, the area parameter, it's pi divided by 2 here. You can also ask Pulsar to draw it out to get a visual feed. If you're using Pulsar Studio, this step is really not necessary, but it can be interesting. You can do that for both the amplitude and the detuning to illustrate that we really define the truncated Gaussian and the linear one. And you can create a pulse based on the amplitude and detuning. So putting together amplitude, detuning, and for local channels, the phase, you have designed the full parameterization of the laser light that would need to be applied to the specific channel. So you can concatenate them into a pulse object. By defining the amplitude as the waveform, you have defined the detuning as the waveform, and for local channels, giving meaning for the phase as well, that you can draw, which will concatenate the two graphs essentially in this representation. Again, this sort of representation is used for the pulse-based objects. You need to add it to the sequence in order for it to appear as a step of instruction for the whole implementation. So what I'm doing here now is I'm simply just adding this newly defined pulse, so this concatenated pulse-based object that had our previously defined amplitude and detuning parameters into channel 1. And once again, I can ask for a text-based representation to give me an idea of what's happening in the different channels so far, or I can simply draw it out to get better visual feed. And now we are seeing something that we have seen on Pulsar Studio in terms of visualization. So we had our constant pulse on channel 0, and on channel 1, we defined this more complex laser pulse for the interaction. Then what you can do as a follow-up is you can also reuse the already defined pulses. So for this complex pulse, so having the truncated Gaussian as an amplitude and a linear detuning, say I have defined it as an object, so I can reuse it for the different channels. So here what I'm doing is I'm adding this pulse for another channel. However, I'm also mixing it in another feature that I mentioned beforehand, is that for local channels, you always need to define which physical qubit you are targeting. However, this definition is not something that's set in stone, so you can dynamically alter the target of a specific channel. So you don't need to define as many channels, as many local channels as qubits you would have. Ideally, you would want to define a convenient number of channels. So if you need to distinguish between Raman, so low energy excited states, and Rydberg, so high energy excited states, you would at least want to have those two channels there already because they are physically behave differently. Otherwise, you might want to have some extra local channels, depending on the type of experiment you design. However, you can dynamically alter the targeting of a specific channel. So this is illustrated again with the target command. I'm setting the channel 0's target, which was initially 1, to 4, and adding this complex pulse. However, what happens here is that my sequence so far contained a constant pulse for qubit number 1, and this complex truncated Gaussian-based waveform for qubit number 4. If I allocate for qubit number 4 a new channel as well and design a pulse, of course, there could be some kind of conflict because I'm trying to target the same qubit with two different laser pulses at the same time. So this is handled by default, as it's mentioned here, with minimum delay type protocol. So what happens in this case is that the program adds your new laser pulse after the execution of the initial pulse on the other channel. So it detects until when you have activity on a specific channel, and then you can chain the activity on top of that. So it does not fuse, it does not overlay by default the laser activity. It queues them one by one in a logical manner. So this is the default protocol that's automatically done at the first availability of a specific qubit that you're trying to target. It will concatenate the laser pulse afterwards. However, you can play around with these protocols if you want a different behavior for your sequences. There are different protocols available. Again, the documentation, the online documentation gives you an exact idea what these protocols can look like. And this is something that you can manually set when you add any given laser pulse into your sequence. So here, to illustrate, I'm going to reuse the simple pulse, which was the constant pulse, and adding it to channel 1, following both the min delay and the undifferent, so wait for all type protocol. And again, with the printing command, you get a textual representation, or with the draw command, you get a visual representation of what's happening. The minimum delay added the sequence at its earliest availability. The wait for all waited for all the other sequences on all the other channels to happen before applying a specific sequence. There is, of course, the possibility of forcing you to execute as soon as possible, so no delay type protocol. So I'm adding a new complex pulse targeting 0 and on another channel, which will force the sequence built to target and execute a laser pulse on the same qubit. So now I built quite a complex sequence of laser pulses that I'm fairly certain has no practical meaning. It's really just to illustrate the different tool sets. And what you can see here is that both channels 0 and 1 will be targeting qubit number 0 at some point and with 2 specific frequencies. So each channel, in a sense, corresponds to a specific laser. So this is something that the machine is physically capable of carrying out. However, how the dynamics would work if you were to employ 2 separate laser lights at the same time is quite complex. So this functionality is typically not recommended unless you really know what you are doing on the back end. Nevertheless, with the emulators, you're welcome to play around to see what kind of complex dynamics you can instill for the experimentation itself. Again, the tool allows for it, the programming tool allows for it because it is physically a permissible activity, even though from an implementation perspective, there could be some very, very limited ways to actually apply it. Once you are done with designing your sequence, you need to put an end to it in a sense, like with all quantum computing-based programming paradigms, you need to do some measurements. So you need to do some observations for this. As it has been illustrated, pulsar, much like neutral atom systems, supports all permissible bases. So it supports the ground state, the Rydberg type hyperexcited, so high energy states, as well as the Raman type low energy states. So measurements can be done using one, the other, or all of the energy states in mind. This is something that you need to specify for the tool when you want to ask for measurements. So here, with the supported basis command, you can, much like with the available channels, query what kind of measurement bases are available. So the digital refers to ground state and Raman, so low energy measurements, low energy state measurements, and the ground Rydberg refers to ground state and Rydberg type hyperexcited state-based measurements. What has been chosen is this ground Rydberg type measurement state, and therefore it puts at the end a visual block representation indicating that's the end of your sequence. And at this point, the tool is making a measurement based on allocating zeros to ground state and ones to the Rydberg hyperexcited state. For a digital, it would be able to detect low energy states as one already. It leads to a different type of measurement basis. And if you want a mixture for a specific device, that's also possible to distinguish three different states in a sense. Although you do need to design algorithms that support those three different states. So with that, I've reached the end of the introduction side that I wanted to mention on Pulsar to give you sort of an overview of most of the bases that are available in designing an experiment, a Pulsar-based experiment. Again, as you can see, it's a very, very low-level interaction because you are really working with the signals. So it's lower than gate-based interaction in a digital setting. It's the natural environment for an analog type interaction, but it really requires you to get and to have some understanding of either the operator-based formulation or the physics of the system to be able to properly design the experiment. Barring that, the emulator-based toolkits or Pulsar Studio allow you to experiment with different layouts, with different setups to try to optimize it, to try to optimize the layout or the pulse sequence itself to get the best results possible. I don't see questions for now, so let me move on to the last part of what I wanted to elaborate for today, which is a specific experiment that was designed based on what we discussed on Friday about independent set solvers and maximum independent set solvers in particular. So here, the idea is that we are given a graph, any kind of graph in actuality, but we are going to work with a very, very concrete one. So a graph is a collection of nodes and edges, and we are tasked in finding certain nodes such that no two of these nodes are connected, so there is no edge between any of the selected nodes, and we are trying to find the maximum amount of set nodes corresponding to the maximum independent set or MIS problem. So as it has been alluded on Friday, this is one of the staples, so go-to problems for a neutral atom system, because it's relatively simple to encode this problem for a neutral atoms device. Despite the fact that from a classical computational perspective, it is still considered a hard problem. So from a complexity theory point of view, it's what we call an NP-complete problem to find this maximum independent set of the graph. However, for quantum computers, especially for neutral atoms type systems, the problem becomes much easier. The reason for this is that if you look at this maximum independent set problem from combinatorial optimization point of view, we can define a very specific cost function to this graph. So here I've written out the mathematical representation using indicators. So the Z's are indicators, having one SL value if they are selected as part of the independent set, otherwise having 0 SL value. And the cost function, in this case, that needs to be minimized, is designed by having individual contribution of each selected node, and then penalized by the number of edges running between them with a very, very large coefficient. So the first term corresponds to the individual effect of adding nodes. So this just adds up how many nodes you have with a negative coefficient. So the more nodes you add to the selection, the lower this number gets. The penalty term corresponds to whenever you have edges. So whenever there is an edge between the indicators I and the indicators J, then you add a specific large constant that increases the cost function's amount. Therefore, this cost function naturally favors the fact that you have the largest number of selected nodes having no edges in between them. Because if you have no edges running there, then this will result in a zero sum, so you won't have this large penalty term taking place. So this is a combinatorial optimization-based representation of the maximum independent set problem. And why we are using this is that we can see some interesting similarities between Ising-type Hamiltonian formulations or in general operator-based representation of the problem that naturally arises when you are dealing with analog-type quantum computing or with neutral atoms-type systems. The first term here corresponds to the one-body interaction terms, while the second term corresponds to the two-body interaction terms, which for a neutral atom system is dictated by the geometry. So the second term, this penalty term, is given by the geometry itself. The first term is just for the natural selection. As an example, to illustrate how you can design an experiment to find independent sets, we have seen the antiferrometallic state experiment as one, but here I've selected a very, very specific small graph as an example. I've tried to choose a graph that's at least not trivial to solve, but it's still something that's relatively easy. So you can, of course, solve it by hand to find independent sets. But interestingly, you can also use it as a base to experiment with the platform a little bit more in detail. So, as we have seen with previous discussions, the experiment starts by designing the atomic register itself. So for that, I need to take this selected graph representation and encode it onto a quantum register. So the coordinates were known, therefore I can just simply use basic coordinate-based encoding. I will be choosing the labels myself, so I'm not expecting the program to allocate labels, but I could do that as well if I wanted to. So I simply indicate this dictionary to the register of pulsar, the register object of pulsar, to generate this atomic representation. What I've done on top of what we've seen beforehand is that I've added some extra parameters in the draw function in order to have a better highlight of the atomic register. So if I go back to my initial example, when I asked to just draw the atomic register, what it would do, it would draw dots at the specific coordinates in the Cartesian coordinate system to indicate where you would want to have atoms. However, I can spice up this draw command by adding some extra geometric features. So here in this case, from the digital analog device, I'm recovering the interaction distance. So the readback blockade radius is the limit up until which atoms can interact with each other, in a sense. So I can recover this readback blockade radius and use it as a geometric parameter to draw these circles that have appeared here, that offer a physical geometric representation of which atoms can enter into interaction with which other atoms. Based on this, I can also do a graph-based visualization. So to not only have nodes, but also to have the edges drawn between nodes that are sufficiently close together based on the blockade radius defined here. So I can really make the geometric representation much more meaningful if you put some extra geometric parameters into the fold. Once I have the register itself defined, the next task for me is going to be to define the pulse itself and the sequence on which we want to rely on to carry out the experiment. So I will start from the bottom to explain the logic. Once again, as we have seen, we need to define the sequence. So we need to define the series of laser pulses with which we want to interact. We are going to use a single global channel, so the simplest implementation that can be made compatible with the current physical device as well. I'm using digital analog device to keep in line with what we have seen beforehand, but you could also use the analog device as well. So a single global channel is going to be used, meaning that I will need to design laser pulse that will be seen by all of the atoms at the same time. So that's why it's a global. What's the laser pulse I'm choosing? I'm choosing, in this case, interpolated waveforms. So an interpolation-based laser pulse in which the amplitude gets gradually increased up until a cusp, a maximum value, and then gets gradually decreased. In the meantime, the detuning parameter changes sign with a linear evolution from a negative value to a positive value. This type of sequence, we have seen it in the example, we have seen it last week. It corresponds to what we call an adiabatic type evolution, which instills a slow evolution by gradually increasing the amount of energy the system gets in order to excite the whole atomic register at the same time. So the main driver here is the amplitude, for which I've chosen a value that corresponds to the geometry itself. This is for this that I have some mathematical background that I need to incorporate because I need some values to be chosen according to the experiment I want to carry out. So the main driver in this experiment is the amplitude. So I need some considerations on what should be the maximum value of this amplitude. For this amplitude, I want to choose a value that somehow features, somehow encodes the geometry and enhances the interaction between atoms that can interact, while inhibits interaction between atoms that cannot interact. For this reason, I'm basing my interaction, my amplitude parameter on two factors. The first is what's the largest distance between atoms I have in my register that are still connected, and what's the smallest distance between atoms that are no longer connected with each other. So in this example, atoms 0 and 3 have the largest possible distance. It's the same distance as 0 and 4. and larger than the distance between this equilateral triangle 0, 1, and 2. And the smallest distance that has no connection is between 2 and 3. So as you can see, the two circles are not connected, meaning that Rydberg blockade radiuses do not reach each other, so they cannot enter into interaction. That's why there is no edge drawn in the graph representation. I'm going to use these two values to define a specific maximum value. I will put it somewhere in between these two to get a good quality result. And for the detuning, again, the important part was for the detuning to just change sign. It's not that important to have a specific value for it. So I have chosen -5 as a default initial point, and +5 will be the target at the end. But this is something that can be changed or looked at to optimize. However, an important factor that we are going to come back to is the time. So how long the evolution should take place. So as a recap, once again, the three main things we need to keep in mind is the amplitude, the strength of the amplitude, the detuning, the shape and the strength of the detuning, which in this case is not very important, and the length of the experiment. So how long this actual experiment lasts. With these three in mind, I have designed this pulse that is just an interpolation for the amplitude to reproduce this gradually increasing, then gradually decreasing shape. And then for the detuning, it's just a simple linear evolution that has been chosen. Once it is defined, I can add it to the sequence, and then comes the only part that we have not elaborated yet. That's why I wanted to highlight this part of the experiment, is that once you have your sequence ready, so in the sequence, you already have the geometry encoded, you have the device selected on which you want to execute it, and you have added the laser pulses. With that, the sequence object is complete. You can send it to for an actual execution, which in this case is happening with a local emulator. So when you install Pulsar, it comes with different local emulators at your disposal. Qtip emulator is one of the more well-known options. So we are relying on that to run the experiment. So based on this sequence, we load it on the emulator to execute it. And then we can recover the final states that I can represent with this plot graph representation. So what you can see here is I have the bit strings, so the results that come out of the computational cycle with a number of shots that measured that specific sequence plotted here. And I have color-coded with red the two bit strings that correspond to the maximum independent set selection. So these two bit strings, as you can see, they are being featured out of the 1,000 shots in total. Almost 500 times you measure one of them, and almost 500 times you measure the other one. What is this 00111 and 01011? So if we go back to the graph representation, the 00111 also allocates 0 to the qubit number 0 and to qubit number 1, and then 1 to the qubit number 2, 3, and 4. So it provides a selection of the atoms 2, 3, and 4 as a potential maximum independent set. And as we can see in our graph, 2, 3, and 4 nodes are pairwise disconnected. There is no edge running in between them. The other bit string that came up with a very, very high probability was the 01011. So selecting qubit number 1, 3, and 4, which corresponds to the other potential solution. So this execution clearly highlights that our experiment is working as intended. It managed to select an independent set with a high number of nodes selected, which for this simple graph corresponds to a maximum independent set problem solution. And finally, this is something that you can design. I wanted to illustrate more the results than the actual code, is that when you design an experiment, you have different parameters that you need to consider. You need to consider the amplitude, you need to consider the detuning parameter, and you also need to consider the duration, especially with adiabatic evolution. So for slow evolution, time plays an important factor. For this reason, what I've done here is I've re-executed the same experiment, but instead of using 4.5 microseconds, I've defined different time parameters. So I've redone the same pulse for different durations, going from 1.5 microsecond all the way to 6 or 7 microseconds. And I've plotted the quality of the results for each duration. So I'm using the same sequence, but for different durations. The shape is the same, it's just the duration that changes. And I'm measuring how well I am able to find, how likely I am to find the right solutions out of all the bit strings that come out. And as you can see, and this is a typical curve that you get for this kind of experiments, is that if the duration of the pulse is too short for an adiabatic evolution, it cannot take place if you were executing too fast. Therefore, the solution becomes super noisy. So the quality here of the solution is very, very low, as you can see. As I increase the time, the quality gets increasingly better, and it reaches almost a plateau at almost here I'm measuring with approximation ratio, but it's really just the quality of the solution that starts peaking at 4.5 microseconds. And 4.5 microsecond was the parameter that was chosen for the experiment. This is the advantage of working with emulators, is that you can run these kind of optimization cycles, trying to identify which is the parameter regime that is likely to produce the best quality solutions. Here, what you need to take into consideration is that, yes, for adiabatic evolution, the longer you do it, typically the better it gets. However, there is the other side of the coin, so the physical constraint that on the physical machine and therefore on the devices, there is a maximum duration that is defined. So you cannot keep atoms excited indefinitely. There is decoherence that's happening naturally, so the experiment cannot take too long, otherwise physical noise will start playing a role in it. Here I was working with a simple Qt-based emulator, but it did not consider any kind of noise effects. However, Pulsar allows you to put what we call a noise model into the emulation. So I can load not only my sequence, but a noise model as well that simulates actual, in a sense, real-life behavior with specific instructions on how noise evolves. And with that, you can test your code, you can test your sequence on really a digital twin of the physical device, or in actual real conditions with noise acting on your system, which would then give a very, very different picture on how the time evolution looks like for adiabatic evolution. But in general principle, the idea behind adiabatic evolution is it needs to be a slow evolution to guarantee good quality solutions backed by this brief analysis on the solution for different time spans as well. But for the actual machine, you need to consider the other side, that noise will start taking an increasing effect the longer you execute your computation cycle. So there is sort of a trade-off that you need to account for when you are trying to find the right parameters of the sequence. For the time, it's much more apparent. For amplitude and detuning parameters, it can be a bit more tricky. Therefore, much more investigation and experimentation is in order to try to find the best possible parameters to guarantee the best quality solutions. So with that, I've reached the end of what I wanted to share with you for this more of a deep dive session. Again, most of what we discussed is available in the different Pulsar documentations. In any case, if there is a need for it, I can also share the Jupyter notebooks. I will discuss with the organizers what would be the best way to do that file sharing for you. And I think there are a couple of questions still. So how can you delete what you have added to the sequence? So there is a remove command that allows you to remove part of the pulse, or you can just simply, if you haven't gone too far, you can just redefine the whole sequence. But there is a remove option, much like there is an add option, there is a remove option if you have added an undesired element. There is also ways to modify existing components of it. That would require for you to label, in some sense, the different components to be able to access it. But if you have done the labeling, you will be able to go back and modify parameters of an existing part of a sequence as well. So are there cases when approximation ratio is less than 50%, even if the time evolution is longer? Yes, that can very well happen. So again, time factor is just one factor of the experiment. There are other factors that play into the quality of the solution. So I didn't detail it too much, but there was a choice that needed to be made when designing the maximum amplitude. And technically, you have a choice in designing the detuning as well. This is one of the simpler examples, but you can create something much more complicated. And depending on the choices you make in selecting the amplitude's form and values, the detuning's form and values, that will have an impact on the quality of the solution. So if you haven't designed your experiment correctly, you can end up with a laser sequence that is simply not solving your problem, in a sense, or solving your problem, but with a very, very bad efficiency. And in that case, no matter how long you are executing the sequence, it might not improve the quality beyond a specific threshold. Typically, for these small registers, so I'm working with 5 atoms, it's a very, very simple design. So it's unlikely that you will bump into a scenario where no matter what you do with the pulse, it doesn't increase consistently the quality. However, for larger number of qubits, so for more complex geometries, geometry itself will start playing a more important role. So typically what can end up happening is that the quality of the optimal solution might not increase because your solver, as I mentioned, favors in large independent sets, but it does not necessarily favor the maximum independent set. So if you design graphs that have a very particular maximum independent set, but a lot of other large independent sets, your algorithm can end up favoring these suboptimal solutions instead of the actual optimal solution, which would technically reduce the quality of the or the value of the approximation ratio, in a sense. Nevertheless, it would still provide you good solutions. It just would not necessarily favor the best solution. So really the simplest case I can think of is a graph where you have a particular maximum independent set and a couple of large independent sets that are not that are maximal, but they are not the maximum independent set solution. So with 8 to 10 node graphs, you can definitely design such examples. And for that, it's highly likely that your algorithm would favor the large independent sets without in particular favoring the maximum independent set. So if you have multiple combinations of good solutions, but only one right solution, that would drastically decrease the quality. But that doesn't mean that the solution is wrong or the algorithm is wrong. It's just, it really functions as intended, selecting large independent sets. And that's what you really need to keep in mind on a more algorithmic layer, is that adiabatic evolution on graphs really tends to favor large independent sets by default. So in this sense, strictly speaking, it's not a maximum independent set solver, it's a large independent set solver in a sense. So that's what the physics actually dictates here. Are there any other questions? Yes. So this is the fact to have large independent sets that are not maximum, only maximal. So what we discussed on Friday, this slight subtlety, a slight difference between the two notions is what you run into from optimization point of view with barren plateaus. That's exactly that. And to counteract this, for this adiabatic evolutions, actually noise can play in favor of it. So extending the duration to a slightly noisy regime can potentially help you bump out of a barren plateau. So that corresponds to quite a few stochastic methods and random walk-based optimization algorithms that try to test random directions in an optimization cycle in order to avoid falling into a local minima or local maximum, local extremum, for instance. And for the physical machine to have noises, you can use it to your advantage to avoid this in a sense, or at least try to avoid it. Yeah, so for the measurement, again, the measurement, let's go back to the image itself. The measurement works as follows. So you are essentially taking a picture of your atomic register in which you are looking at your atomic register and trying to detect photons that are emitted by the atoms in a natural way. So at the end of a computation cycle, you have excited your system. So certain atoms might have received sufficient amount of energy so that they are allowed to leave the trap. So at the end of the experiment, there are certain trap placements that no longer have the atoms because they became excited enough to leave the trap, to allow to leave the trap, while atoms did not reach sufficiently high energy state, or it was not long enough for them to actually leave the trap, so they stayed in the trap. In the fluorescent imaging, when you measure the photons, you can only detect atoms that are still in the trap itself. So what you will see in this fluorescent imaging is that you will measure the photons emitted from atoms that are in the trap. So do you know that these atoms stayed in the trap? They haven't reached a sufficiently high energy state. Therefore, they are closer to the ground state. So you allocate a 0 to these bright spots. So these atoms that show up in the atomic register. However, you will see dark spots in placements where there was an atom initially, but the atom has left. And therefore, the atom has left because it has reached a sufficiently high energy state, meaning that it was close to the Rydberg hyperexcited state, which is the one reference state. That's how you distinguish between the two. So that's the potential advantage here, indeed, that this large independent set selector or maximum independent sets type solver, technically the duration, once you have fixed it, stays the same independently of the instance itself. So the only thing you need to increase with the increased size is the number of iterations. If you have designed the experiment well enough, you don't need too many iterations because with a high probability, you can guarantee a good quality solution. So if you're able to have this kind of repartition where with almost 100% likelihood you fall into one of the two potential solutions, this is a very, very good indicator because that means that, for instance, 9 out of 10 executions or 10 out of 10 executions will reach one of these two quantum states, which is a good solution for your problem. So designing an optimal shape allows you to guarantee good fidelity for the precision, and then you can leverage that to scale up the solution itself and therefore providing a much faster or a much better quality solution for an MIS type solver. If there are no more questions, I think we have reached the end of today's session. So I would like to thank you all for your attention once again. And for those of you who can connect.
Krisztian?
Yes?
Yeah, this is me, Hee-jung. I think there is one more question in Korean. Have you seen that?
Yes.
Yes, I can just simply translate it. Yeah,
Thank
if
you.
there are any, if there are any advantage when we execute measurement when the amplitude is maximum. Is there any advantage to measure it when the amplitude is maximum? I don't know if I understand the question, by the way.
So physically, what will happen for this is that when you do the measurement, for that, you turn the lasers off. So there is a couple nanosecond grace period when you turn the amplitude down back to zero physically. So on the physical machine, that's what would happen. In actuality, you can stop the experiment there, but typically, once you have reached maximum amplitude cusp, what you have introduced is a large amount of entanglement to your system. So you can use this to do some random selection. So if that was the purpose of your algorithm, that can play into your advantage, and you can leverage that to stop the experiment once you have excited the system, not allowing it to relax. That introduces a high entanglement, so you will do some quite a random measurement. But algorithmically, it really depends on what's the objective. So what's the problem you want to solve? For a maximum independent set selection, it's important to relax then the system for it to reach one of their stable energy states that provide for a good selection and not just a random selection. If you want to experiment with this, I recommend wholeheartedly to look into the Pasqal Studio tool because that allows you to stop the experiment at any given point. So you can physically stop the experiment when you are at the cusp, when you are at the maximum amplitude to see what has happened. And what typically happens is you have sort of a mixed state of all the individually excited atoms without having potentially more meaning to the system than that. Yeah, thank you, Hee-jung.
Thank you for answering. Hi.